Hey folks, and welcome back. This is now the fourth video in which we develop a driving AI system for the game I'm working on. And I'm hoping to actually wrap the AI work in this video, at least for now. Because these systems tend to get really big and complex over time and require lots of iteration. And it's probably not very interesting to see on video. So while the AI work will by no means be done after this video, I think we will move on to other things in video form, and I will continue working on the AI system and probably show it off to you every now and then. But I wanted to end this small mini-series on a high note and actually get AIs on the screen. So what I decided to do was I spent a few hours prepping for this video by porting over some of the systems that I have in C++ to Zig, so that we just have to neatly tie it together in this video and we can play around with the system a little bit. So without further ado, let's go through what I have done since the last video. We have this new type called driveline, and it's actually not really a new type. As I have explained in the previous videos, I'm porting over some of these concepts from a C++ iteration of this system. And the driveline is ported over almost verbatim, because it works really quite well in the C++ version. So what is a driveline? Well, it is essentially a nav mesh query on steroids. So when a vehicle wants to go somewhere in the world, it starts by beginning a new driveline. And it lets the system know where it wants to go, how close to the destination point it needs to be considered at the destination, and the vehicle radius of the vehicle itself. And this vehicle radius is used for nav mesh queries, so that the system knows how large the vehicle itself is. And the nav mesh is something that we haven't really played around with in means at all. And to use a driveline, you need a nav mesh, so we're going to have to actually generate one today. And once you have begun a new driveline, you call tick on it every update, essentially. You let the system know where the vehicle is, how its orientation is, and the linear velocity. And the system then figures out if it needs to find new raw paths, so new nav mesh paths. It does some processing on them. It figures out if it needs to update the target point, and then lets you know when the vehicle is at the destination. It also does some other things like calculating vertex scores. So the raw nav mesh path is obviously just a set of positions. But the driveline also contains things like speed multipliers, so that the AI vehicle can slow down a little bit if there's a lot of cornering, things like that, and then speed up again as the path is more straight. And so this class is essentially doing all of that and some additional helper things. I'm not using all of the features that it actually provides currently, but they're kind of nice to have there. And like I said, they work pretty well in the C++ version. So the next thing that I did was the whisker system, and this is something that we talked about in the previous video. The whiskers are essentially a set of raycasts that the vehicles can use, or the AI vehicles can use to detect if there's something dynamic in front of them or behind them. So things that don't show up on the nav mesh can be detected using a whisker array. And we're probably not going to get to whiskers today. I think that's something that I'm gonna have to put in later. But yeah, this is also a type that I ported essentially as is from the C++ version. This is essentially just a glorified set of raycasts. You can see here that calling tick on a whisker array does a bunch of raycasts. So we won't actually go further into this today. then we get to something that's a bit closer to what we worked with before, so actions. In the previous video we had this dev action, so development action, which you can now give to an action scheduler, so essentially an AI brain, if you will. It has a list of tasks that needs to carry out, and these tasks are represented by an action. And this dev action essentially just printed some things and stopped itself when it had been running for 4 seconds. So we have a new move to action, and this now uses a new component which I'm going to show you in a second. But basically you create one of these guys, you set the same parameters essentially as, they're actually not exactly the same, but almost the same parameters as you give to the driveline. You tell it where you want to go, you give it a movement profile. This is just an enum, calm, normal, or fast. How quickly do you want to go there, essentially. And then the same arrival epsilon. And this thing, when it starts, which is something that the action scheduler will do, it uses a new driving component to pass those things to. And the driving component allows you to set a callback. So when the movement is essentially finished, or if it failed, then you get that information as well. So here we have the movement callback, and you get the result there from the component. Okay, what happened? And either we succeed or we are interrupted, and this information is then passed on to the action scheduler, just like it was with the dev action. So this is kind of how we hook the driving and moving somewhere in the scene into the action scheduler. Anyway, I spoke about this new driving component. This is probably the most complex thing in this body of work that I created. And this thing has a bunch of data, as you can see. It has an auto gearbox component. Oh, I'm clicking on things involuntarily. It has an auto gearbox component, the vehicle controller component, has the vehicle controller itself. It has a finite state machine. And this is something that I'll get back to in just a little second. This is actually really cool. So propagated values, so acceleration, braking, steering, whether or not it's active or not, things like this. Then some other boilerplate stuff. And this critically also owns the driveline. So the driveline is sort of like the minimum you'll need in a system like this to actually drive the vehicle somewhere. As I get the whisker systems and all kinds of obstacle avoidance and whatever else I want to put into the actual driving, that stuff is going to go here just next to this driveline. But using this driveline alone, we should be able to get vehicles moving and driving around the scene. Not being super smart about it, but yeah, maybe smart enough to actually be kind of fun to play with. And so this system is essentially taking the information we pass to where we want to go, how we want to get there, etc., and feeds it into the driveline, and then takes the driveline. So you can see here that if we are in the state, again, I'm going to get back to the finite state machine in a bit, but if we're in a state where we're following the driveline, here we're ticking the driveline, we're getting some updated steering values. Here's some commented out code. This is C++ code that I just haven't ported over yet. So speed lowering logic, for example. This is the kind of stuff that I'll get to later at some point. We forward it to a speed controller, and then we set some propagated values, because this thing now obviously also needs to get networked, but because you want to see the wheels get like the front wheels, the steering, you want to see it on the client, for example, and AI runs on the server. So that's where a lot of the complexity here comes into. Yeah, we have some reverse turns. these are also not implemented yet. As we saw in the first video on the driving AI, the C++ version in Project Slide actually knows how to do reverse turns, things like this. This is handled by this reverse turn logic here, which I haven't put in yet, but I left a place for it here. So that's kind of nice. And then we check, are we at the destination? Has the drive line failed? Things like this. So this component contains quite a lot of things that, well, I won't go into detail now. We can look at these things individually later. And of course, you're very welcome to ask if you're interested in something in particular. Now, the state machine here is kind of interesting. So let's look quickly at the AI driving component. This is essentially like the same class or same type in C++. And I implemented a state machine framework a long time ago, actually, for Basis, which allows us to model these state machines in a slightly more formal way and have the state machine issue callbacks when something happens. So we have like state inactive, following drive line, reverse turn, stopped. Then you have transitions between those things, and you have actions that you can send to the state machine, and then you sort of hook it up like this. So you add the transition, start moving from inactive to following drive line, for example. You have essentially like the whole flow of the system here in one place, and you can somewhat easily see how it's set up. Well, I was wondering how I would implement this in Zig, and I actually found a third-party library, very nice, called ZigFSM. Now, this is the first third-party code that I'm actually putting into means now. I have another string library on the Basis, the engine side. But I integrated this into the game code because this solves almost exactly the same issue that issues or problems as my own state machine library does in Basis, the one that I used for the C++ version. And now I can use exactly the same thing, or almost exactly the same thing here in Zig. So super nice. My states here, I have my events here. I call them actions. ZigFSM calls them events, but they're almost the same thing. And you can map the whole FSM onto into like a table form like this, where you tell it like, okay, there's an event, and if you are in the inactive state, then you go to the follow driveline state. And if you issue the move to event when you are in reverse turn, it also goes to the driveline state. And so this is the whole flow, and allows me to build these things, these behaviors, in a very similar way. Then you can have an on-transition event that fires, and this works a little differently than my own system. I had like exit and enter handlers that I could set for specific things. Here you essentially have to handle it with a switch case, but it works just as well. So pretty nice, pretty nice. And yes, with these things in place, the only thing we really need to add is the brain itself, the brain component. I've spoken about this elusive brain component a few times previously, and today we'll actually implement it. And it should be actually reasonably simple to add now that we have all these other things. So what I'm thinking is this. We'll create a component that has an AngelScript interface. So we can script a vehicle in the game to go somewhere. And actually we can sort of queue up locations. So we can tell it to go here, and then go there, and then go there, and then go there, etc. And all of this will be very easy to do thanks to our action scheduler, because as you've seen in the previous videos, we can have multiple actions queued up, and it will carry them out one after the other, and it can even do multiple things simultaneously on different layers, but that's not something that we're going to do today. So a simple component with a scriptable interface which simply adds these new move to actions. So this thing that we looked at previously to the scheduler. And that should really be everything we need to get cars driving around. So I'm gonna implement the component now, and I'll talk more in a bit. All right, I think we're done. Remains to be seen if this works or not. But this is pretty much the minimal version of this that I can think of. So we have the actor context and action scheduler here. In the previous video, we created a component, an actor component, which contains basically just these two guys. But I think I kind of would like to have these in the brain component itself. This way we don't have to have an actor component just to hold these two guys. So I moved them here. Let's see if this is what we'll end up with. Then we just have a boolean here, whether or not the brain is active or not. So the reason we have this is that a vehicle object can be controlled both by the player and by the AI. And so by default, the brain is actually turned off, and only if the player is no longer using it will it be turned on, or it can be turned on, shall we say. And that way we don't get conflicts between the player's inputs and the brain's inputs. All right, so then we just have the script code as we need to do if we want to script it. We have the exposed property map, which we need to have if we want to script it. And we have the register angel script function, which we need to have if we want to script it. So I added these three scriptable functions here. Set brain active, as we discussed, we need to enable it or set it to active before we can actually issue any orders. And this is of course the interesting one for today. Move to object. Takes in a game object target and tries to get the position of that. Clear layer is just, you can just clear a layer here. I have an int here because we haven't really exposed the layer enum to AngelScript, nor will we probably do that, but you can do it here with the number. And these are bound just to these wrapper functions. The wrapper functions then call into the sort of public API. So you can call these things, set brain active, move to objects, or clear layer, both from AngelScript and from Zig. If you just want to use this component directly from code, you can do that as well. It has a public API like this. You can write like public API or something here. And yeah, so this is reasonably straightforward. If you enable or disable the brain, we clear the layers. If we disable the brain, it makes perfect sense to clear the layers. We want to stop any ongoing actions. Probably also if you want to enable it. There shouldn't really be any actions, but it doesn't hurt to clear it. So I didn't put any if here. I just always clear them. And yeah, clearing the layer is doing the exact same thing. Then we have this interesting thing here. So move to object. So we get the target, and we get the target as a game object, a const game object in reference, which is like an AngelScript thing. And here in this wrapper function, we take that and turn it into a string, basically. So the path to the object that we want to go to. So what do we do with that? Well, first of all, we take the game state, which contains information about all the objects that are in the game world at this point. And we use the game state to get a pointer. As you can see here, it's an optional game object pointer to target object. Then we check, is the target object something, or have you given it like a bogus path? If you have, then go here to else and just print to the screen invalid target, no such object. If we have an object, we try to get the world transform out of it and put it into position and orientation. So world transform returns a boolean whether or not we could actually get the transform, because not all objects in Basis actually have transforms. You can create an object that is purely logical and has no physical or spatial information at all. So if it doesn't have one, it prints invalid target, no transform. And then finally, if we do have those, this is where the fun stuff begins. I'm going to actually build this now. It takes a little while to build the release while we speak. So we take the action scheduler and we append a new move to action, and I just put it on the primary layer for now. I think this is probably a primary thing to do, is to actually drive somewhere, and then smaller things go on the secondary layer if you have that. And right, so we append it, but it's not started yet. That's something that the scheduler will do when it's time to do that. After we have appended it, we get with the pointer so move to action pointer, and we can set the parameters. So here we set the position, the profile, and I just use the fast profile here. Probably that's the most fun one, so obviously I do it. And then arrival epsilon as well. So it needs to be within 3 world units of the target to consider it done, so to speak, and get on with its other tasks. Right, so what else do we do? Well, we do the get on object created resolve pointers here, which resolves the driving component. So we better actually have one of those driving components. And that's why I need to... oh, actually, no, this thing doesn't use driving component. The move to action uses driving component. And yeah, this gives us an assert if you try to do that and you don't have a driving component. So that's fine. It should give us a clear error message if we don't have that. So now the only thing that we need to do is to add an AI brain component and an AI driving component to one of the vehicles. And then we can script the vehicle to do things. So that should be fun. Let's go into the asset browser. And here we go to vehicles, vehicle blueprints, and we added to our trusty test vehicle. I think testing out with something like the mother vehicle as a first test will be pretty catastrophic. So let's use the small and nimble and well-tested test vehicle for now. Right, so one of these actually already has or is registered here. So if we type AI, we should get means.ai driving component. And the reason I went ahead and registered this already previously is that it has these blueprint properties. So you can set these values here. Interestingly, it cuts off the text. So this just says front whisker min length twice. That's supposed to be speed, but it cuts it off, apparently. Anyway, calm speed, normal speed, and fast speed. These are kind of the interesting ones to us right now. So fast speed, it should drive at 70 kilometers per hour, basically. And then slow down in certain places. So that's one thing that we need. Then we also need this new thing, which isn't registered yet. So I'm going to copy this text here and go back to the browser and do component, and we can just call this AI brain. And yes, it's not registered, but that's fine. We only want it on the server. It actually won't do anything on the client. So cool, that's it. Now that we have this on the server, if we now go into the level, the same level that we've used for a while, the test vehicle should be scriptable. So that's exciting. Might also just crash and burn. Let's see what happens. So we can go here all the way to the beginning, I think. And we have this guy. And yay, it's now scriptable. And now if we add like a test function to ourselves here, so what do we call this? Drive something. So the first thing that we need to do is we need to enable the brain, set brain active true. And yes, we get nice autocompletion now for these new methods that we added. So where should it go? Let's have like a reasonably short distance for it to drive first, so that if something goes wrong, we don't have to like drive all the way across the map to figure that out. So let's call this like AI test, something like that. And yeah, this should be auto-loaded. And I think we'll use our diamonds for this as well. These diamonds, even though they were sort of created for just a very simple throwaway game mode, excuse me, they have proven to be very, very handy indeed for all kinds of things. Right, so it should drive to this diamond and then stop, basically. So right, let's try to make that happen. So move to object, and the object is called level objects dot AI test diamond 1, and that's it. And now if we try to run this, it won't work because we don't have a nav mesh. So let's add a nav mesh to the scene, and that can be done simply by adding a nav mesh object. I typically add it to the base layer. Doesn't really need to go on the base layer, but typically that's what I do. We have all kinds of settings that we can tweak here, and we might have to tweak some of these. But let's just see what happens. So let's try to build the nav mesh. This can take a little while, especially if you have lots of really high density data. Right, so we get some errors there. Too many walkable platforms. Yeah, it's reported as an error, but it's not really an error. Just one of these areas that have like, well, probably tries to generate nav mesh in some really weird places here. We can actually, let's see if we can put the draw offset a bit higher. So because the nav mesh doesn't follow exactly the geometry of the level, you sometimes get these weird like holes in it because it just intersects the geometry. Here you can see actually that this is weird, right? The nav mesh just has almost like a jump here, and I'm sure you can understand what that is if you've seen my previous videos. That is the test mission geometry, which we can unhide here, and whoop, there we go. And you also have these things cutting holes in the nav mesh there. Well, we can quite simply mark these as not being nav mesh blockers, and then we can hide them again. And now if we rebuild the nav mesh, those holes should go away. Not sure if I really need that test mission there anymore, but it can be quite handy to have, I guess. All right, rasterizing tiles. Any minute now. And there we go. And now we don't have any holes anymore. This is actually kind of stupid. So the diamond cuts a hole into it. That might actually be a problem for us. Okay, so let's go and actually fix that. Those aren't primitive geometry objects though, so we need to find the gameplay blueprint here. It's actually it was in minigame, and we have a toggle here whether or not the mesh component blocks the nav mesh. So let's just untoggle that. And we have to re-initialize the engine to reload the blueprints like so. And now we can build the nav mesh again. That should hopefully be the last thing that we have to mess with to get the nav mesh working correctly. I mean, it might have worked even without all of that, but since we're actually trying to find a path to one of those diamonds, if the diamond is in fact not sitting on the nav mesh, then that's probably going to be a problem. And now we can see that now it is. And it looks like it's kind of underneath it, but that's just because we lifted up the nav mesh a little bit. So just put it down, you can see that it is there. Yeah, 1.5 is maybe a little too high. Let's just raise it or lower it a little bit. Okay, cool. So with a little bit of luck now, it should the car should start and drive to the diamond and stop. Right, so we can still actually have the camera connected or looking at the vehicle, and we have this drive thing here, and hey, would you look at that? And it stops. Right, so it doesn't really doesn't really brake hard enough to actually stop, but it works. Pretty cool. You're just gonna have to take my word that I didn't actually drive the vehicle. I know it's kind of difficult to see that kind of thing on YouTube. But if I now take another one of these, or put another one of these down, place it like there maybe, and then there, something like that, and then I just add more of these here. So we can add any number of these guys, of these commands, to the car, and he should, if everything goes correctly. Hey, look at that. Yeah, the steering is a little weird. It sort of looks like someone's playing with a keyboard. Right, we should see the... Yeah, we get we get so we can actually run this again now, right? Drive, yeah, there we go. So starting move action, you can see here, and you get move action finished, and then it starts another one. Pretty nice. Yeah. And then the last one. And then we run out of steam. Okay. So pretty nice. Pretty nice. The first movement AI working, well, essentially how I wanted it to work. Really cool. So last thing I wanna try today is let's say we put another one of these guys over here, and we play this thing. And so I'm sure you can imagine what is going to happen. Oh, I probably didn't script it, did I? Did I script the thing? Probably didn't. No. Well, then nothing would have happened, but let's see. Put it like that. So let's just make sure that this works first, and then try to get fancy, or then see if we can get fancy. Yes, so it does seem to work. I don't know why it's choosing this exact. Oh no! Oh, yeah. The pipe is not actually drivable, so it's a hard collision but it actually handled it pretty well. It might actually have been sort of in the worst case scenario would have been with the nose against this pipe and then would have gotten stuck. Because we don't have any of that collision detection stuff there yet. If we look at the nav mesh here, yeah, the nav mesh kind of looks like it's that is traversable, but obviously it's not so. So that was a little bad. But what if we wanted it to actually drive along this road? So it would pick these guys, and then it would go to the road, and then it would drive up here, and then to that thing. Like how can we do that? And that is where that cost area cost thing that I mentioned previously comes into play. So I haven't tried this, but I've used this extensively with the C++ version. So I hope my driveline now works the same way and works correctly. We can create a new layer here. The layer doesn't actually even need to be loaded during the runtime, because this is an editor-only thing. So we want a nav mesh area path object. And a nav mesh area path has a control point type name, common waypoint, right? So we can simply have one of these guys. We need to add these to the same layer as the nav mesh area path. So let's do that. Let's start adding these things. You can see this path now appearing like so. And you can continue it this way if you want to. That's fine. Let's add another layer, and to this layer we will add one of these nav mesh area paths as well, and then start adding waypoints to that. And so what this does is it allows us to set the area type on the nav mesh. And you can see here there's a drop down. It's set to road by default, because that's typically what these paths are used for, but you can set it to other things. And when the agent chooses the path, or rather when the nav mesh returns the query path for us, it tries to use a path, or tries to return a path with the lowest cost. And we set the cost down to 0.3. So I'm going to show this again to you. Let's go to driveline. We can search for cost. So the area cost for the road, again here we have the nav mesh area type for the roads, and the road navigation cost is set to 0.3. Normally it's 1, so everything costs 1. But here we are setting the roads to cost only 3, which means that if the well, you can consider it sort of like how much fuel is going to be used, or how much battery power in an EV is going to be used to actually drive somewhere, and it's cheaper to drive on the roads, which means that the nav mesh will then return the path with that runs along the road, and this area path simply you need to place as many points as you need for it to cover the areas that you're actually interested in. So here, for example, you can see that it has these circles. And the circle defines the thickness, so you can make it much wider if you want to. And now this whole area is covered by the road type. Typically, you don't want the nav mesh road to be as wide as the road actually is. You just want like a very thin strip in the middle, because that is then the area that it will sort of aim for. And here I think that we should add another point here. Let's add one there, and then we need to actually move it up in the hierarchy to have this. Don't we? I think we do. Yes. Oh, there we go. I just didn't regenerate it for some reason. Yeah. So right, it can go through the ground. It doesn't really matter. Now that we have these areas set up here, when we actually, so we can draw the nav mesh again. Now that we generate this, we should see the roads show up in a different color. And they will tell us that we have laid them out successfully. And then you need to make sure that they are wide enough so that they cover the areas that you want and nothing more, essentially. It takes a little bit of practice to get these areas sort of correct. All right, so here we go. We have this reddish color here. These might actually be even perhaps slightly unnecessarily wide, but it's probably fine. If you make them really thin, then they can sort of break, even though it doesn't really matter. But it can be a little annoying to an OCD person like me. Okay, so now that we have these things in the nav mesh, the only thing we really should need to do is run the game. We don't need to actually tell the system to actually use the roads, because the driveline sort of already does it. So let's see what happens now. Like, obviously, it needs to drive off the road when it needs to go to these diamonds. Okay, so nothing happened. Yeah, so now we ran into the actual problem that I was afraid of. Actually, okay, well that's annoying, isn't it? That's annoying. Let's move this a little closer. It might just have been that it didn't want to take the road because it was sort of would have had to go a bit further from it. But I think it should want to actually use the road. Let's see, drive. And we can, of course, yeah, that was weird. Yeah, now it can't actually, it probably can't reach that thing, right? It just runs around it because it is sort of aiming for it. I think the road calculation sort of threw it off there. So now we would have to have actually some logic here to determine that, okay, the turning radius is too large now. We need to sort of slow down, right? All right, so it reached it eventually, but it took a little while. And do we have the same problem here? Maybe. All right, it reached it. I think at least it looked like it reached it. All right, so now it Yeah, it doesn't want to take the road still. That's sort of annoying. Don't drive into that pipe. Yeah, there's clearly some work here left. But that's to be expected. This still works really quite well, in my humble opinion. Let's try to see what happens if we just tell it to go to the diamond 4 directly. We have these other diamonds here that sort of mess with it a little bit. Does it actually drive along the road now? Yeah, see, now it drives along the road. I don't know what that was, but okay, yeah. Okay, keep going until you reach the junction. Keep going. All right, and now it should turn. Yeah. All right, cool. And then at some point it decides like, okay, the road continues, but I need to turn now, and that's when, yeah, there we go. Right. Okay. All right. So as you can see, like it's a bit tricky to get these costs right. Let's see one last thing. This is the fun kind of game development where you just play around with things. Let's make the cost of the road even smaller. So let's make it something like 0.01. And see if that helps. Because apparently it sort of decides to just run straight to the final point, and that's not good. So it should at least make it a little better if it's virtually free for the agent to move there. We still, of course, have the same problem that we did previously with this starting problem. But I moved it onto the road now, so let's see what happens. Right, so now it wants to stay on the road until the very end, and then it does this thing. So yeah, that's annoying. Let me just speed up this part for you a little bit. All right, so yeah, it still wants to take this route. I don't know why. It's probably gonna. No, it went quite all right. So yeah, there's something there that I need to tweak a little bit. But basically it works. It just sort of works in a somewhat unexpected manner. But it does work. And obviously I didn't write the code that actually selects this path. It's part of the recast and detour package that I use to generate and query these nav meshes. So that would be that. Yeah, I think even though we had some issues getting it to do exactly what we wanted, the AI is kind of brain dead still. The driveline doesn't really is not really enough for it to make a really intelligent driver. It needs a lot of special case handling. In the C++ version in Slide, it's already a lot better, but even that would probably need some more work to make it good enough for shipping. But yes, I like this architecture now with these actions, with the action scheduler, a lot better than the C++ version, which uses the behavior trees. And I think I'm kind of more motivated to iterate on this thing now, because this is so simple, and there's no third-party code to worry about this time around, except Zig FSM, which is actually super awesome. So this thing here, very nice third-party state machine framework. Anyway, I'm kind of rambling now. I kind of consider this a success. I hope you found this interesting. Lots of work still to be done. But then again, we created an AI system from scratch, basically. So that's just to be expected. I expect to show this system off to you in future videos, hopefully in a much more polished state. But yes, I'm going to leave the AI, at least in video form, here for now. And if you have any questions or suggestions or feedback, leave that below. Remember to smash all the like and subscribe buttons. And I hope to see you in the next one. Bye.